Okay, now we're good. On whenever the last time I saw you was, Tuesday, we left off here and I said, hey, go do these. And you went and did them. So let's talk about one of them. I probably also said, yeah. Yes, I do. I probably also said something like, do this the same way you would do an absolute value inequality. Which means first we want to solve the equation. The inequality sign is tricky, right? It does weird stuff sometimes, not always in predictable or easy to explain ways. So to avoid that, we just say, well, forget it. Let's solve the equation instead. That's a little more straightforward. X squared plus 6x plus 8 equals 0. Everything's already on one side. I've got it equal to 0. So we're good to go to either factor or to use the quadratic formula, right? Either one of those is perfectly fine. This factors nicely. Factors of 8, well, 1 and 8, 4, 2 and 4. I want them to add to 6, so 2 and 4 would work. So this factors as x plus 2 times x plus 4. And then the zero product property says that either x plus 2 is 0, which happens when x is negative 2, or x plus 4 is 0, which happens when x is negative 4. Okay. Once we have those, that tells us where these things are exactly the same, right? Where is x squared plus 6x plus 8 exactly 0? Well, it happens twice. Once when x is negative 2, and again when x is negative 4. In other words, what we just found are the x-intercepts of this function, right? If I think of y equals that thing as a function and graph it, it's a parabola that opens up. And what we just found are its x-intercepts because we set it equal to 0, right? What we're looking for is where is it less than 0. So to solve the inequality, basically going to do what I always do, draw a little x-axis for myself. What I just figured out is that negative 4 and negative 2 are the places where interesting stuff happens. That's where they intersect. That's where it's the same as 0. That's where things can change. Those are going to be the endpoints of the intervals where the inequality is solved, where the inequality is true. I can do one of two things. I can either think graphically about what's going on or like plug in test points and just do the arithmetic again, like we did with the absolute value stuff. If I want to think about the graph, all I really need to know about this is which way it opens. Right? It's a quadratic, so it's a parabola. Which way does it open? Up, because that term's positive, right? So missed, but there we go. I can fix that. It looks like that. You know, not exactly. I'm not being real precise with it or anything, but that tells me enough. The question is, where is the function less than 0? Well, here's the x-axis. That's y equals 0, right? So what does it mean to be less than graphically? Above or below? Below, right? Less than, below. So where is this inequality true? Here. So the solution is going to be negative 4 to 2, right? It's not true out here because out there the graph sits up above the x-axis. Here, though, that's what we're looking for. This section of the graph sits underneath the x-axis between those 2 points. If you don't like that and would rather test points, then test points instead. We know what the answer is going to be, but I could pick things like -5 and -3 and 0 and plug them in and see what happens. -5 squared plus 6 times -5 plus 8. You got to do a little bit of arithmetic, right? That's the price you pay for it. But 25 minus 30, -5 plus 8 is 3. Is 3 less than 0? No. Same thing here. Plug in. It is less than 0 there. 0 I can do. Plug in 0, I get 8. And no. Again, like the absolute value stuff, it's almost always going to kind of alternate, right? True, false, true, or false, true, false. But again, we want to actually like think about and test all 3 intervals, because starting next week or so, it's not going to be true that things are always like alternating like that, right? So patterns are always, we want to look for patterns, but we also want to be like kind of wary of patterns, right? So actually check all the intervals. But then our solution set, everywhere that was true, well, that was true between -4 and -2, and brackets or parentheses. Parentheses because strictly less than, not less than or equal to, so it's not included, right? So open interval. Okay, so what about this is different than the absolute value inequality problem that you did on the test a week ago? Basically nothing. Yeah, right. Basically nothing. Exactly. Right. Basically nothing, except for like this first step, right? How we actually solved it. Well, before we were solving an absolute value, so you solve it like an absolute value. Now it's a quadratic, so we solve it like a quadratic. That's the only thing, though. This part, we're doing the same thing, right? I could, with the absolute value stuff, I could have thought through it graphically, or I can kind of manually like brute force it by plugging in points. The same thing's true here. The same thing's true everywhere else. Once we decide about which intervals actually work, we write them down as intervals. I will just say this, don't write anything down, but the thing with absolute value where, not everyone did this, but a few, where you can sort of split the absolute value up as long as you're careful on one side to like flip the inequality, like that whole thing, that does not work here. So you cannot, just because I got to this factored thing less than 0, you can't split those factors up like that. This doesn't work. Because we're talking about multiplying 2 things and getting a negative number back. If you multiply 2 things and get a negative, either this one was negative and this one was positive, or vice versa, right? So to make that kind of looking at the individual factors, splitting it up thing work, you have to be thinking about what both of them do simultaneously and making sure one's positive and the other's negative, and then vice versa. And like it's just way more involved than it's worth, right? You have to be juggling like 4 separate things in your head at the same time to figure out where it's true. And then you have to do an intersection of the sets, and like it's a whole thing. So not worth it. Don't do it. And this is more straightforward and generalizes better anyway. So there you go. There's another one there in 8 that you can try on your own. And then number 9 again is an application where it's mostly about figuring out what we need to look for. Maximum height in part A, so we need to find the vertex. No one catches the ball, then where does it hit the ground? What do we need to do? The function is height versus how far it's traveled, so we need to find the x-intercept. which would mean taking the function setting it equal to 0 and solving. You can do that by hand with the quadratic formula. You probably don't want to get into trying to factor that because the coefficients are a mess, obviously. You could also do it graphically. This thing looks something like that. You're probably going to have to mess around with, Windows stuff a little bit to see it, but you're looking for the x-intercept, right? This would be where it hits the ground. Graphing calculators, Desmos, whatever, everything's got built-in, stuff to help you find points like that. If you want help with how to do that, I can show you how to do that sometime. And then where did he throw the ball from? That would be the y-intercept. So again, a big part of it's about, just the interpretation aspect and deciding what do I actually need to look for here? None of finding the things once you know what you're looking for, none of that should be all that difficult. If you're doing quadratic formula with this, it gets a little bit messy, but just punch it all into a calculator basically, because you're just going to round your answer anyway. Everything else is fairly straightforward to find. Okay, does anybody have any other questions at the moment? Okay. Today, our last bit of kind of new stuff for this week. We've seen a bunch of different kind of perspectives on how solving equations works, how we deal with quadratics. Everything has kind of been set up so that we're answering those questions when things are nice, when things go smoothly. This is kind of going to get into a little bit of, well, what happens when things don't go quite to plan. Because we're dealing with functions that have a square in them, and we've seen in a few different places that, not always, but often, we end up needing to deal with a square root then in the process of solving. Like, think about the quadratic formula, right? Part of it is that big square root term in the middle, right? Pretty hard to miss that. Well, that b squared minus 4ac underneath, that's called the discriminant. But this thing has subtraction in it, right? B squared is always non-negative, but we're subtracting something from it. This could end up being negative, right? This whole thing could be negative. If that ends up being negative, then we're dealing with the square root of a negative number. The square root of a negative number is, well, not defined, maybe in some sense. It's different, right? I don't know how to deal with that. So let's take a look at, a sort of simple example of something where that comes up. X squared plus 1 equals 0. That's a quadratic equation, right? It's got a square term in it. I'm setting it equal to 0 and trying to solve. What can we do to try to solve this? Okay. If I subtract 1, I get x squared equals negative 1. That works here, right? The subtracting 1, because it's just the x squared term. I don't have like a square and a linear term to deal with, just the 1. Well, then what? If I want to get x by itself. We've got x squared, so take the square root, right? Like we talked about yesterday, when you take the square root of x squared, there's kind of an absolute value thing happening. That means you get a plus or minus there. And this is where things get interesting, because I've got plus or minus the square root of negative 1. And if I try to just take the square root of negative 1, like somebody have a calculator handy? Well, anyway, if you actually punch the square root of negative 1 or any other negative number into a calculator, what you get usually for most calculators is an error message, 1, but it'll say something like error, non-real answer, right? So there's an answer. It's just not a real number, right? To deal with stuff like this, we have to kind of extend our notion of what it means to be a number, what it means to count. Because there's nothing that I can square, no real number that I can square and get -1 back, right? That's not how it works. To deal with things like that, though, we define a new thing called an imaginary number. The imaginary unit just means 1 in a math context. So the imaginary version of 1, which we write with a lowercase kind of script I. You just want to make sure that your I doesn't look too much like a 1 or doesn't get lost or confused with something else, right? So I'm going to write it as like a cursive I, make a big dot, whatever. Just make sure you can tell what it is. Imaginary, because it's not real, right? There's a cute little math pun happening here, right? It's not a real number, so it's an imaginary number. It's going to act like 1. We're going to call it I, and the way we define it is as the square root of -1. This lines up with real numbers because what's the square root of 1? 1. So the real number unit, right? The real version of 1 is 1, but it's the square root of 1 also. So this is defining it the same way, but for a negative number. Okay, well, if I is the square root of -1, what's I squared? It'd be the square root of -1 squared, right? What happens when you square a square root? You get rid of the square root, right? You get rid of the square, you get rid of the square root. Those are opposite things. They undo each other, no matter what was underneath it, right? So the square root of -1 squared is not 1, but -1. Remember, these are new. They're different. They're weird. Weird stuff is going to happen, right? It looks weird to say something squared equals a negative number, right? There's a weirdness about that. Well, there's supposed to be. It's a weird new thing, right? It's an imaginary number. So because of the way it's defined and because it kind of runs exactly counter to what we know about squares and square roots and negatives and stuff, then yeah, okay, I can buy that this, sort of feels backwards. How about I cubed? How would you get from I squared to I cubed? No. How do we get from I squared to I cubed? How do you add 1 more into the exponent? This means I times I, right? And this means I times I times I. Okay, so multiply by I again. So I squared is -1. If I multiply this by I get that. If I multiply this by I get negative I. Multiply by I here to get from squared to cubed, which means you multiply by I here to get from -1 to negative I, right? Or opposite of 1 if you want, and opposite of I, right? In the sign sense. Okay, what about the 4th power? Do it again, right? What's negative I times I? It's negative from that, and then I squared, right? But I squared is -1. So that one would be 1. And then just around and around, right? If you want another way to think about the 4th power, take this and square both sides, right? I squared would be I to the 4th, and -1 squared would be 1. But then again, it just like cycles through this, right? So I is this sort of weird interpretation of 1, which is why 1s keep showing up in the powers of it, right? It's this weird way of breaking 1 down. And because of that, powers of it, I see 1 showing up. I see -1 showing up. I see I showing up again. It just cycles through after this. But that means I can figure out things like I to the 37th. I don't have to just count them all. How many times does 4 go into 37? 9. So 4 times 9 is 36. Just for emphasis. 37 is 36 plus 1, right? Well, I to the 36, this is just going to do the same thing as I to the 4. So what that means then, that 37th power is just going to go through this whole cycle 9 times. And then there's 1 left over, right? So if we go through this whole cycle 9 times, that's 1. And then this 1 left over, this would be the same thing as just I to the 1st. So we get this weird thing happening where, I can basically look at, once I get my head around this idea that, it's 4s, right? That it sort of cycles through. I can look at something like the 37th power, the 742nd power or whatever. And if I can figure out how many times it goes through 4, right? And then what's left over, I can tell you exactly what that is in terms of either I or, 1 or -1. Okay. Now, apart from just kind of knowing what it is, we're going to do a little bit of arithmetic stuff with imaginary numbers. And that's mostly so that we can deal with them when they come up in solving a quadratic. And that's pretty much it. So how would the square root of -16 work? Now that we know how to deal with the negative part here. It'd be 4i. That's I times the square root of 16, but the square root of 16 is 4. So it's just 4i. The same thing is true elsewhere. So basically, we just take the stuff that we've been doing lately about simplifying square roots and looking for factors inside them and stuff, and add a layer to it that, okay, well, if there's a negative, that means there's a factor of I. Right, so the same thing's true here. This would be I times the square root of 20. And then I can break the square root of 20 down, as usual, right? The way you would normally deal with the square root of 20, which is 2 square roots of 5 times I. Or 2i root 5, or I times root 5. There are lots of ways that you can, arrange that because it's just multiplication. None of them really look that good, but just make sure the I is, outside of the square root. That part's important. Okay, so I times the square root of -50. Well, there's the I that was already there. And now there's another one from the negative under the radical. And then I have to deal with the square root of 50, right? So how does the square root of 50 break down? $50 is 10 is 2 and 5. So it's 5 root 2. So it's I squared times 5 root 2. But I squared is -1. So it's negative 5 root 2. Okay. So there's that. Now these numbers are all, or the first two that have an I in them. This square root of -4, square root of -16, square root of -20. Those are all what's called purely imaginary or pure imaginary numbers, because all they have is an imaginary component, right? I can write them down in terms of I, and that's it. So there are real numbers like 5. There are imaginary numbers like 2i. Often though, we have a number that's got sort of both, right? It's got a real part and an imaginary part. We call those complex because it's got real and imaginary stuff. A complex number just looks like this, where that 2 is just the number 2. That 3i is, again, this imaginary, 3 copies of this imaginary unit. But there's a real part and there's an imaginary part. And we just write it, the standard thing is to just write it as a plus bi, so real part first, imaginary part second. Sometimes that's called standard form for a complex number. A plus bi, real plus imaginary. So here the real part is 2, the imaginary part's 3. Here the real part is 1, the imaginary part's -5, right? And so that last one, the real part's 0, so it's again purely imaginary. The reason I talk about this is because this is relevant for doing arithmetic and stuff. Those 2 components to it, the real part and the imaginary part, we basically treat those like type of term, right? So like you would if it was, 2 plus 3x instead of 2 plus 3i, right? For doing arithmetic, it's basically the same functionally that, the real part I combine with real parts as like terms. The imaginary part I combine with other imaginary parts as like terms if we're doing arithmetic. So if I, add 2 complex numbers together, like in number 1 there, I'm just going to add the real parts and add the imaginary parts. So this would be, well, we're adding, so I'm just going to drop the parentheses. And just add those like they were like terms. So, functionally the same as if they were x's there instead of i's. Add those together. 2 plus 4 is 6. And 3i minus I is 2i. That's it. So y'all give the next 2 a shot, 2 and 3. Okay, so in 2, we're subtracting 1 minus -3. All right, those are the real parts. So 1 minus -3 is 4. And then 2i minus -i would be 3 of them. So plus 3i. Okay, what about 3? Sorry, number 3. Now we're multiplying, and we're multiplying 2 complex numbers. So basically, we need to treat these like binomials, like we would if it was, x plus 1 times x plus 2. So we have to do a binomial expansion or a FOIL, right? Expand this whole thing. So -2 times 4 And then the outer part, -2 times -2i, so plus 4i plus 12i minus 6i squared. Then what can we do? Combine. Combine what? Four and 12i. So 16i. Okay. Can we do anything else? Again, that's exactly what we would have ended up with if it had been X's or T's or something instead of I's, right? But I is different. That was a fun sentence. I is different. Bad grammar. I has a special meaning, right? I is the square root of -1. What's I squared? -1. So that minus 6i squared, that's not an imaginary term. It's got an I in it the way it's written right now, but really that's a real number, right? It's camouflaged, but really that's a real number. That's 6 times -1. So really we have -8 plus 16i minus 6 times -1, so that's plus 6. So -2 plus 16i. Answer and like look at the directions there. Write the results in standard A plus BI form. Your answer to a complex arithmetic thing should be a complex number, which means it's got at most a real part and an imaginary part, right? It's possible that only one of those shows up or both, but I can't leave I squared, I can't leave I cubed, I can't leave I to the 37th because I can reduce those out, right? We know how to deal with we are figuring out how to deal with those. Okay. The last one there, 4, those both have a negative under the root. So you can factor an I out of both of them. And then go from there. I times I is I squared. Square root of 3 times 6. So the square root of 18. See if you can reduce that at all. I'll leave that one for you to kind of finish up because I want to talk about division. Addition, subtraction, multiplication. Well, addition and subtraction is really just, like other algebra stuff, like combine like terms. That's not a big deal. Multiplication, well, multiply the way you normally would, but if powers of I show up somewhere, then just remember that we can reduce those out and combine stuff down a little further. Division's weird, right? Division's always kind of weird. It's sort of weird with real numbers because at the very least we run into the thing where, well, if I want to divide by 0, I can't because what does that even mean? But think about what this is asking you to do. I know how to divide 5 by 4, right? I have 5 cookies. I have 4 friends. Everyone gets 1 1/4 if I'm going to share them equally, right? What the heck would it even mean to divide by 3i? Like to split in an imaginary number of pieces, right? Like that doesn't really even, I don't know how to conceptualize that. I don't know how to get my head around it. And it's not just that even. I'm dividing by 4 plus 3i, right? I'm dividing by a complex number. It's even in the name. Like they sound scary by the name we've given them, right? Complex numbers. They sound like they're going to be hard to deal with. So dividing by a complex number, I don't know how to do that. I don't know how to make any sense of that. So what we do, and this happens, kind of a lot in math stuff, is I don't know how to answer that problem. So I'm just going to not answer that problem and go around it. And the way we're going to go around it is by rewriting this thing so that I don't need to know how to divide by an imaginary number or a complex number anymore. I'm going to rewrite this so that I'm only dividing by a real number. Because I understand how to split a thing into 4 equal pieces, even if the thing itself is weird and complicated. The way we're going to do that is using, so we did completing the square a minute ago, right? And the trick to completing the square was adding zero, adding the right kind of zero, and then, balancing it out, borrowing, and whatever. The flip side of that, the other way to do something like that is to multiply by 1. You're always allowed to multiply by 1. So what we're going to do is multiply this by 1, just the right kind of 1. We'll see, as we go, why we do this. But I'm going to take the denominator here and multiply by 4 minus 3i. Okay, if I do 4 plus 3i times 4 minus 3i, what do we get? Actually, multiply it out. 4 times 4 is 16. Squared on the last one, right? Yeah, minus 9i squared. Okay. So cool. We just, expanded that product out. What happens though? Positive 12i minus 12i is 0. So those cancel, those drop out. Okay, that's good, right? Less stuff is I'm always good with, fewer things to write down. And they were both I terms, so those are gone now. What do we still have though? 16 minus 9i squared. But what do we know about I squared? It's -1. So what are we actually dividing by? 16 plus 9, right? We're dividing by 25. I know how to divide by 25, right? I can split a thing up into 25 equal parts. Oh, sorry. So this weird thing that we did here, where we multiply by a thing that looks kind of like this, but what's different about it? That sign in the middle. And the reason that I want that sign in the middle to be different or opposite is so that this will happen. This is called the complex conjugate, this thing we multiplied by. Doing that, which again feels like a weird step, at first, right? But doing that lets me rewrite this thing in the denominator and just get a real number back, right? Just get 25. And again, I know how to divide by 25, but I don't want to change everything, so I have to do it in the numerator also, right? This is 1. It's just a weird way to write 1, right? But the top and bottom are the same, so that's just 1. I'm multiplying by the right kind of 1 so that the denominator turns into a real number, so that I get a thing that I know how to make sense of, right? I know how to divide by 25. In the top, you do that multiplication, you get 20 minus 15i. Excuse me. But I see lots of stuff that's divisible by 5. So we can reduce. And again, here, just like we talked about on Tuesday, might be helpful to think about it that way for reducing. 20 over 25 is 4/5. 15 over 25 is 3/5. And the goal, as pretty much always with complex arithmetic stuff, is to take the thing we started with and figure out how to rewrite it as a complex number with just one real part and one imaginary part added together. So look at 6. What do we need to multiply by there to get the ball rolling? 2 plus I, which means we have to do that on top and bottom. We always want to look at the denominator to decide what this thing's going to look like, because that's where the problem is, right? I don't know how to divide by an imaginary number. So fix the denominator so that it's not imaginary or complex anymore, right? Rewrite the thing so that I don't have to do that. So you can finish that one. 7 and 8. This is kind of back to why do we even care about this, right? Why did we go do this whole little side trip into complex numbers? Well, because they can come up in solving quadratics. So here are 2 quadratics to solve. They're probably not going to factor nicely. So you're probably going to want to use quadratic formula. And you shouldn't be surprised if it shows up with a negative under a square root somewhere, because now you know how to simplify and break that down and write that. Take try those two. Sorry. We've sort of covered everything for, stop this.